Hello, my name is Orhun Aydin. I'm a senior researcher at Esri and I'm a lecturer at Spatial Sciences Institute of USC. Today I will talk about spatial data science, its transformative power for our planet. What is it? What is it not? What is it? What does it involve? And I will also talk about exciting new research avenues that is in this field as it pertains to spatial problem solving. I have to start by saying that I'm very excited to be, even though it's virtually, be with you today on the Geospatial Summit because it brings us together from such wide disciplines and interests. Whether you are a geodesigner or a city planner who wants to make sure that public transport runs smoothly, or if you are a hydrogeologist digging wells in remote parts of the world to make sure that everybody has access to water, or if you're working on precision agriculture, or if you're an epidemiologist or a planner who want to make sure that um, there are required hospital resources during the COVID-19 pandemic, we all use spatial data science in one form or another. We work with spatial data, we have analysis goals and research questions in mind, and we solve these research questions and achieve these goals through the use of spatial analysis. A big part of spatial analysis is data. So I would like to first talk about spatial data and its growth, and I will follow this up by spatial data science, how it can ingest such data, what we can do with spatial data science, and what are some of the questions that we can answer. I would like to start with this seemingly outdated slide. This was a forecast for 2019 of what 2020 was going to be like by Microsoft. And they forecasted the amount of data that was going to be produced by different devices that we use. So here you can see some unconventional data sources like autonomous vehicles, stadiums, smart homes, or personal devices. At first sight, it may not seem like none of this data is spatial, but remembering that all of these devices have spatial aspects to them. A lot of them even have GPS trackers in them. We see more and more that these devices do produce massive amounts of spatial data. In addition to producing spatial data, such data can open up opportunities for mapping and also opportunities for modeling phenomena that may not have been possible with more conventional sensing devices such as satellites. If you have if you have data from autonomous vehicles, for example, we can have very fine scale data of the road network from LiDAR images, from dashboard cameras that would otherwise not would have been possible. In addition, if you would like to understand agent-based movement patterns, the personal device data that is produced is massive and is at a very fine scale. That being said, not all of this data is available for analysis at large scale and for good reason, especially due to data privacy reasons. But the data that is available can definitely open up analysis opportunities. Now, moving forward from this hindcast of 2020 to the forecast of 5 short years, when we look at spatial data, we really expect it to grow. So this is a projection by Seagate, and where they're talking about how we produced 9.5 zettabytes of data during a pandemic. And this data is just going to increase more and more. I have to I have to be honest and say that these data volumes, the 51 zettabyte that is projected to be produced in 2025, is not all spatial. This is all of the data that we produce. And when we look at some of the numbers, some of the big drivers of this data set, for example, tweets. At the current rate, there are about 500 million tweets a day. And about 1% of those are geotag tweets. And this number is expected to grow, both nominally and also in terms of the spatial portion of this data set over the years. So we will get more and more spatially enabled tweets that we can process to understand, to basically perform social sensing tasks. In addition, even the more conventional data sources, such as satellites, are getting even larger in variety and volume. We have seen a rise in microsatellites in the past couple of decades. So the number of satellites that we can launch and the ease with which they can be launched is also becoming quite favorable over the years. And of course, this data set is growing in variety. In addition to this conventional data source, we have an unconventional data source that I think is going to be used quite often, such as data from autonomous vehicles. The sensors that are attached to these vehicles are mapping our cities at a very fine scale, and being able to ingest this data set is quite important. And of course, we have a variety of IoT devices that produce massive amounts of data in dimensions um, in dimensions that were not really possible in the past. Being able to sense data such as consumer behavior or overall preference of the AC use in an area. This can be quite important for predicting things like electricity shortages, potential electricity shortages at certain periods of time. So this data is becoming more and more available, increasing in variety and in volume. So now that these data sets are becoming more available, I would like to talk about how this fits into the entire idea of spatial data science. And this is basically the outline of my talk today. I will talk about spatial data science as this function. Um, and if I had to just point to it, I would like to talk about spatial data science, almost like this mathematical function that takes this input, which is open data. And here, open data is quite important because if data is openly available to all of us, then the research can be reproducible, the work that we produce will be reproducible, and it can be extended easily by others. So here, spatial data science is really this analysis framework, is analysis, a set of analysis methods that turn data, and this being spatial and this being quite impactful for many different aspects of our lives, I will take a leap here and call that our planet's memory, to turn it into a nervous system for our planet. Basically taking a research question and a data set and turn it into a set of actions. So this is basically the main promise of spatial data science. So this being said, I would like to talk about what spatial data science is, talk about what it isn't, and also some how it fits into the entire scheme of problem solving. First and foremost, when we think about the workflow, um, where we start and where we would like to go, we basically start with a research question, just like any other or an analysis goal, just like any other analysis project. And then we basically go through these steps of cleaning the data, wrangling it in a format that we can work with, exploring, exposing patterns in this data, then modeling observations in this data set, and then making predictions to understand, to make forecasts and to basically make predictions where we don't have data, to finally be able to make a decision about our initial question. So this is the main premise, and this is the main workflow that we follow in spatial data science. This may not be news to most in this summit because we have been doing spatial analysis for decades. We might not have called it spatial data science. And I will point out to some nuances between what we mean with machine learning and data science. But before I do that, I want to talk about how this fits into the entire enablement from large data, how this knowledge can be extracted using spatial data science, and where spatial data science fits into a larger framework of informing others through analysis. As I mentioned, we start with our research question or our analysis goal, and after we collect data, the data can take many forms, such as spatial temporal, spatiotemporal, tabular, any other data source. And then we basically look for analysis frameworks. These can be languages, programming languages. These can be platforms like the ArcGIS platform. And once we're using a set of analysis frameworks, we tend to find the relevant tools in these frameworks quite fast. We build an analytical pipeline, and then this analytical pipeline in the end serves data products. These can be maps, widgets, apps, so on and so forth. So I would like to give this holistic view of where spatial data science is, basically in this whole analysis framework and developing methods or developing workflows using these methods. Because the importance here is spatial data science really allows us to go from data and with the right workflow to a data product that we can use to make a decision. It will not automate all of the tasks that a human being needs to do, but it can definitely produce very informative data products. I think a striking example of this came during the pandemic, where I believe all of us at some point looked at the GHU map of COVID-19 cases, in which case they did summarize the data spatially, temporally, and they symbolize it in a way that everybody can understand it. So there you can really see the importance of these data products, and you will, I think all of us appreciate how spatial analysis can really enable impactful data products in that regard. So here the whole idea is going from data to some knowledge that we can also disseminate. So having talked about where spatial data science fits, I just want to talk about some of its components and some of the words that I'm sure all of us have heard, like artificial intelligence, machine learning, deep learning. These are buzzy words that are being used in and out of context. So when we think about how they relate to each other, this basically is the relationship between these three. Machine learning methods are just enablers of artificial intelligence, but they are not the enabler of artificial intelligence. There are different ways with which artificial intelligence or enabling machines that can make decisions or that can create models can be enabled. Machine learning is just one way of doing so. And with machine learning, we are talking about statistical methods that can learn from data, that can perform a task with increasing performance as more data or experience is provided. And inside the umbrella of machine learning methods, we know that there are these deep learning methods that I'm sure all of us have heard of. These are just specific methodologies inside machine learning that utilize neural networks, in the past known as perceptrons, that have multiple layers, decision layers to them. So this is just a very specific type of machine learning method that can do classification and regression tasks. So this being said, how does machine learning, data science enable artificial intelligence? The main point here is these methods can learn from rules and patterns that's in the data. So here we have data explicitly representing, we have the data, but we don't really know what to expect, what to find in this data set. And with these methods, we can find patterns, we can find relationships with ease. And when we think about enabling artificial intelligence via use of machine learning, we're really talking about accomplishing this experience, this task. For example, we would like to detect land cover uses from a satellite imagery, and we have some samples, we have some experience of how these land cover uses should look like given a multispectral raster. And with feature engineering, we basically prepare data for analysis. This is data cleanup. And after the data is in a format that can be used, we use machine learning methods to extract patterns in the raw data set or make relationships. So here, the machine learning methods are, as I mentioned, a set of statistical methods that can learn from data. And once these methods are computed, we basically have the outcome. In this case, in this example, it'll be a classified raster with land cover types. So this might seem very natural, and you might be thinking, well, what is the alternative to this? What is artificial intelligence without machine learning then? So an example of this are, for example, knowledge bases. Again, you would like to accomplish a task, but instead of using general methods on data, one approach was, and still is, creating a large set of rules that explicitly tells the computer what to extract from data. For example, in this land cover type, we might just create these set of rules. If these bands are within these thresholds, assign these pixels to forests. And if they are within this threshold, assign these pixels to a different land cover type. So here, instead of learning these relationships from data, the rules are directly imposed on the computer in the computational unit. So one example of such representations are knowledge bases that have been used quite frequently in the past. They still do have some applications. But here, again, artificial intelligence is enabled because the computational unit at the end using this knowledge base can make some decisions about what land cover uses are in a given raster data set. But these rules are not learned from data. These rules are imposed, and that is the main premise of machine learning: being able to learn patterns from data. And when we think about spatial machine learning, um, similar to generic or non-spatial machine learning, we are really talking about three main tasks: the prediction tasks, classification, and clustering tasks. Prediction is creating a model that can predict data either where we don't have it or at times that we don't have it. Classification is a type of prediction, but instead of predicting a continuous number, with classification we are predicting different types of categories, such as land use categories. And with clustering, we are really looking for organizing and describing data with spatial methods by putting it into groups that have similar values in them, with respect to similar groups. So with traditional machine learning that also accomplishes these tasks, we are looking at methods that do not really know space. They don't know if two data points are nearby because they really have no representation of what nearby is. They completely disregard space. Whereas spatial machine learning methods, they represent spatial relationships such as collocation, such as proximity, inherently at the algorithm level, so that when the data comes in, the method knows whether or not 2 points are nearby, if 2 points are neighbors or not. And just to talk about some specific methods, and this is definitely not an exhaustive list. So in the ArcGIS platform, you can accomplish these tasks via use of what we call geoprocessing tools. And with these geoprocessing tools, you can build a workflow that basically goes from raw data to analysis pieces to product dissemination to data dissemination with the use of web apps and online maps. So this makes the use of a platform quite convenient. In the case of ArcGIS, once your data and analysis in ArcGIS, it's quite easy to connect it to the rest of the platform, where you can ingest more data, where you can create data products, so on and so forth. That being said, there are many other platforms out there for analysis, and this is just an example for ArcGIS. But stepping back and looking at the intersections of some disciplines like GIS, machine learning, and spatial statistics, I would like to discuss some of these as it pertains to spatial data science. So in terms of GIS, representing spatial and spatiotemporal data still requires GIS, making sure we are using correct projections, geo-enrichment tasks such as enriching data with spatial entities like distance features, for example. Even sampling, design, and collecting data is very effective using a GIS, and also mapping our data. And we have some intersections between GIS and machine learning already, where we are using generic machine learning methods to classify objects. For example, the raster example, where we would like to classify land use types. Machine learning methods make these tasks quite easy because even though they are out of the box and non-spatial methods, they can find pertinent relationships between different spectrums of a raster and types of land coverage. Actually, I will go ahead and show you all these intersections instead of going one at a time. At the intersection of GIS and spatial statistics, we still have some traditional methods that can summarize data that you can use for interpolation, like geostatistics, or to summarize your data, like Moran's eye, Geary Seas, and hotspot analysis, so on and so forth. These are more traditional because these methods are really geared towards spatial analysis. And on the other side, we do have intersections of machine learning and spatial statistics method where space is implicit. There are methods such as spatial contextual analysis that fall under this umbrella. And of course, at the intersection of all of it, we have space-time explicit methods where spatial and spatiotemporal relationships are explicitly represented at the algorithm level. I think a very simple example that most of us are familiar with will be geographic weighted regression, where relationships are explicitly represented at the algorithm level. And of course, we have applications of machine learning methods, these non-spatial classification, regression, and clustering methods that are still somewhat useful for GIS workflows. And to give you some examples, again, In the GIS realm, managing and wrangling data, we have vast amounts of functionality there. Summarizing data with the intersection of spatial statistics and GIS. We also have very niche spatial statistical models that are still being used in many different disciplines. The intersection of machine learning and spatial statistics. We have newer methods like spatial neural networks and spatial temporal LSTMs that are being worked on and that are coming to surface. Applications of machine learning to GIS, as I said, for labeling and large-scale classification is being used quite often. So, having introduced spatial data science, I also would like to touch on open data. So we talked about data volumes, but as it pertains to spatial analysis, finding open data is quite important, and making sure that this data can fit in the analysis framework is quite important, because this is how we can enable large-scale problem solving. We need to have the analysis pieces, but these analysis pieces need to be able to work with this vast amount of data that is being produced. So interoperability becomes a big point to stress, and being able to work with different data standards, being able to integrate different software platforms, and being able to leverage different software architectures becomes quite important, because instead of using a single platform, a single offering as a silver bullet, if there are methods that are out there that needs to be used from a variety of platforms, this polyglot approach to problem solving becomes quite important. And in the case of ArcGIS, these are some of the standards and products that this platform works with. So it does enable large scale problem solving. In addition to this interoperability piece, when we think about open data, again, in the case of ArcGIS, we have the Living Atlas that provides a wide variety of spatial data sources that are curated by experts that are not necessarily working for Esri. For example, if you're working with geological data sets, the ones that you will find in the Living Atlas are probably curated mostly by USGS, for example. Regardless, this provides a wide variety of data sources to leverage in analysis. So I would like to end basically by showing some use cases and how spatial is actually spatial when it comes down to data science. So just some examples when we're thinking about prediction. For example, in this case, we would like to predict future climate, and this is an example I will showcase in a little bit more detail. We are talking about finding a relationship between simulated climates at a regular grid, with these depicted at these red points, and matching that to observed climate at weather stations in these dark points here, so that we can calibrate this simulated model, and when we make forecasts out in the future, these will be representative forecasts. This problem of climate downscaling can be achieved by spatial data science, because here we know that the climate at two locations that are nearby is going to be similar. So can we leverage such information by using spatial data science, and what is its impact on the overall prediction performance? In this example, I can say that a simple spatial method cannot perform much sophisticated non-spatial methods, just because representing space at the algorithm level brings quite a bit of parsimony to the statistical model itself. And this is a model that I will talk about in detail in a Python notebook in a little bit. But think about the plethora of problems we can solve. Predicting forecasting is becoming another important aspect. For instance, predicting house price markets, the housing market and the house prices in King County, Washington, let's say a couple of years from now or 10 years from now, is an inherently spatial problem, because certain neighborhoods have different rate of increases of their price compared to others. There are also spatial drivers to house prices, such as proximity to water, whether a house has view or not, and all of these can be represented with a spatial temporal forecast model. So in this example here, we can predict some house prices in certain districts and certain areas, and how they will increase out into the future. Clustering, finding groups in data. Again, the spatial finding spatial groups in data becomes quite important, especially for spatial data. In this case, we have GPS tracks from an app that people use called Waze. This is a navigation app. And in this research problem, we would like to understand where the traffic, where do we have traffic congestion. This can have big implications for geodesign and designing better cities and maybe improving the road network in certain places. When we look at the raw data, which are just GPS tags, it just looks like points everywhere around LA. And this data is obtained between 5 p.m. and 6 p.m. on a Friday in LA County. So you would expect basically traffic to be everywhere. But can we go one step further and turn this data into understanding using spatial data science? We can pose density as this problem where if you have a high number of GPS tracks in a small amount of area, meaning that if you have a high density of GPS tracks, that corresponds to traffic. So we can use a spatial method called density-based clustering to find these clusters in our data. And when we find these spatial clusters in our data, we see some patterns emerging that were not available in the original data set. One thing you notice are these plus signs, are these crosses. One thing we observe in this data set is the highway intersections do have a high volume of traffic congestion. And this is an insight that is possible thanks to spatial data science. And of course, non-spatial methods like classification methods, like maximum likelihood classification, random trees, or support vector machine are still quite important. Even though these are non-spatial methods, when applied properly, it can turn a raster into a land cover type. And this is quite important because doing this pixel by pixel by a human can take a long time. But automating this task using a machine learning method can save quite a lot of time and resources to create a labeled image that we can use in analysis. So with this being said, I would like to end my talk by showcasing how spatial data science can be quite impactful for spatial problem solving. And for that, I will move over to a Python notebook. I will showcase the importance of spatial data science on a spatial problem, and I will introduce the climate downscaling problem, which is calibrating a global climate model, which is a simulation of the climate using observed data from weather stations. You can think of this as a regression model. Is a regression problem where using a model, we would like to form a relationship between simulated climate and observed climate. And using this relationship, we can extrapolate the simulated climate out into the future and calibrate it. And I will do this analysis for contiguous regions over the United States, where I'll basically have 19 predictors from a global climate model, and I will have observed data at weather stations to form a relationship between these 19 simulated variables and the observed temperatures. And I will try some non-spatial models and some spatial ones and compare their results for this inherently spatial problem. Just to take a look at the data, I've already covered this in a slide. We have weather stations that collect data at select locations. As you can see, some of these stations are down, some of them are continuously collecting data, and we have simulated climate at these locations where we have simulations such as wind speeds, temperature, humidity, and so on and so forth. So we have these two spatial data sets. And the first approach that we can do is just a generic machine learning method where we are predicting values. One thing I would like to quickly showcase, even though I ran through quite a bit of this notebook already, is relationships. So we see that the relationships we observe at weather stations and simulated variables, there is some complex relationships globally. There are some variables that are highly related to each other in the dark reds and dark blues, and there are some variables that are not quite related. And this might make the regression task slightly harder. So without any further ado, if I just try non-spatial methods, in particular ridge regression and support vector machine, even though like any other mathematical method, these can be optimized to data. When I do a simple cross-validation, so this is the result I get with a support vector machine. that is prone to overfitting to data. So what does this mean? The temperature profile that I predict is fitting the observed locations very well, but outside of these observed locations, it's not doing a good job generalizing it. And with a ridge regression model, I can capture some natural variability of temperatures, high temperatures in the south, cooler temperatures up north. So these two models used all 19 predictors. One was able to better generalize than the other. Again, an application of non-spatial methods to a spatial problem. What if we used spatial methods? One thing I want to note is, since we know that these variables are highly linearly correlated, for a linear model like GWR, we need to pick ones that are not as highly related to each other linearly. So I go through a scheme and reduce the number of variables. Now I'm working with three variables only, and I'm trying two spatial methods. One of them is EBK prediction and the other one being GWR. And one thing we see here is, even with three variables, with a GWR model, which is a simple linear regression model, we are getting a very useful result in terms of capturing patterns, capturing some spatial variations of temperature over the Rockies with very few number of variables. So this already tells us that using a spatial method can result in a more parsimonious representation of relationships, and also it can be more informative since it's a simpler model. So this definitely shows the power of spatial machine learning methods over generic machine learning methods. They both are useful, but given the problem where we know that space is an important factor, spatial machine learning methods can definitely make a big difference for a spatial problem. With that being said, again, I thank all of you for attending this talk, and I hope you enjoy the rest of your Geospatial Summit. Stay safe and be well.